All right, kids, here's your video for discussion 5.1, all about balancing equations and reaction rates. All right, so let's talk about why we balance chemical equations. So when we're balancing an equation, our goal is to make it so that we have the same number of each atom on both sides of the equation. Essentially, we're just following the law of conservation of matter that says matter is neither created nor destroyed in a chemical reaction. So let me think of a chemical reaction that I like, making chocolate chip cookies. Let's say I'm going to make a batch of cookies, and I use a bag of chocolate chips, and the bag says that I have 200 chocolate chips in the bag. I know that if I use the entire bag, I will have 200 chips distributed among my cookies, because chocolate chips are matter, and matter is neither created nor destroyed during a chemical reaction. Matter cannot just disappear into nothingness, and it doesn't just pop into existence. All right, so when we look at a chemical equation, you're going to see two different things. You're going to see the formulas for elements and compounds multiplied by coefficients. The coefficient will tell us how many of each element or compound we have in the formula. So, for example, we know the formula for water is H2O. If I put a 2 in front of that formula for water, it tells us that we essentially have 2 water molecules. Now, it's actually a little more complex than that, but we won't explore that until Unit 6. Now, we also see subscripts. This number 2 is a subscripted 2. Of course, we know that the subscripts tell us how many of each atom we have within a single molecule. So if we ignore the coefficient here for a second, I know that each water molecule consists of 2 atoms of hydrogen and 1 atom of oxygen. Of course, if I have 2 of them, then I would have 4 total hydrogen atoms and 2 total oxygens. So essentially, to find out how many of each element we actually have, you just have to multiply the coefficient by each subscript. So 2 times 2 tells me here I will have 4, wrong button, I will have 4 total atoms of hydrogen, and even though we don't see a subscript here, if the symbol for oxygen is there, it's inferring that 1 is there. So 2 times 1 tells us we have 2 oxygens. Think about this like automobiles. We all know that the average car has 4 wheels. Well, the question then becomes, how many wheels would we have if we had 2 cars? Well, each car has 4. So 2 cars would have 8, and we're dealing with the same thing here. Each water molecule has 2 hydrogens, so 2 water molecules would have 4 hydrogens. Now, on this slide, I just want to give you some helpful hints. We'll actually probably come back to these as we balance on the next slide. But we're going to always start balancing with elements that only appear in one formula per side of the equation. In other words, let's say you had oxygen in 2 different products, in 2 different formulas to the right side of the arrow. It would be really difficult for you to tell which one you would have to add a coefficient to in order to balance. Usually, you can save those elements for last and they'll work themselves out. So in a special type of reaction that we will explore called a combustion reaction, we're always going to see the elements carbon, hydrogen, and oxygen. If you balance them in this order, carbon first, then hydrogen, then oxygen, you'll find it much easier. Now, when you're doing these types of equations, in Virginia, everybody wants to have whole number coefficients, so no coefficients with fractions. So if you end up with an odd number of oxygens, that means you would have to multiply it by a fractional coefficient. If this happens, simply double all the coefficients and it should work itself out. This step is really important. If you see polyatomic ions whose formulas don't change from one side of the equation to the other, instead of trying to balance the individual elements that make the polyatomic ion up, balance the polyatomic ion as a whole. And again, we'll see an example of that on the next slide. Step 3 is the most important step of all because you can count and check to make sure that you have the appropriate number of each type of element on both sides of the equation. I like to say in class all the time, there's only 2 ways you can lose points when you're balancing an equation. One, if you fail to check to see if you're correct, or if you simply give up. And finally, this is the step that I don't find too important, reduce all the coefficients. So if you can reduce all the coefficients down to smaller whole numbers, it's a good practice to do so. All right, so let's go ahead and practice. What I want you to do is pause the video at this point and try to balance each of these equations. Once you do so, you can come back to check your work and see where you may have gone wrong. All right, so here's the result. Now, the first thing I'm going to do is look at the very first element I see. In the first example, the first element I see is aluminum. There's no coefficient and no subscript, so that tells me that I have one aluminum over here. Now I'm going to see how much aluminum I have on the other side of the equation. When I look here, I see I have two aluminums. Since I have one here and two there, I have to multiply this one by 2 so that it matches. So to multiply it by 2, I simply add a coefficient of 2. Now we can look at oxygen. There's 2 oxygens here and 3 oxygens over there. So recall back to Unit 3 what I said, when you have 2 of one thing and 3 of the other, if you want to balance them by using whole numbers, you multiply the thing that is 2 by 3 and the thing that is 3 by 2. This way, number, coefficient times subscript, I have 6 oxygens over here, and coefficient times subscript, I have 6 oxygens over here. Sometimes you have to go back and reevaluate what you originally did, because once I add the coefficient of 2 in front of aluminum, that now gives me 4 aluminum, so the coefficient of 2 over here no longer matches. Since I have 4 on the right side of the equation, I have to have 4 on the left side of the equation, so I'm going to add the number 4 there. This is where we can check our work to ensure that we're correct. If I have the same number of each element on both sides of the equation, that tells me I'm correct. So 4 aluminum, 2 times 2 is 4 aluminum. 6 oxygen, 6 oxygen. So bada bing, you're good. All right, so for the next example, first thing I'm going to look at is nitrogen. I see I have 2 atoms of nitrogen on there. And in NH3, I only have 1. So let me do that. So I'm going to multiply or add a coefficient. Hold on, I'm going to do it by hand. A coefficient of 2 in front of NH3, ammonia. So now nitrogen is balanced. 2 there, 2 there. Now I have to balance hydrogen. Here I have 2. And here, don't forget, coefficient times subscript, 2 times 3, I have 6 on this side, which means I have to add a coefficient of 3 in front of hydrogen to balance. Again, you can check 2 nitrogen, 6 hydrogen, 6 hydrogen. Very good. All right, now this example is one of our combustion reactions. Notice oxygen appears in 2 different products. So it's best to save oxygen for last. So let's start by balancing carbon. I have 7 here and 1 there, so I'm going to drop a 7 in front of CO2. Excuse me. Here I have 16 hydrogens, and here I have 2, so I have to place a coefficient of 8 in front of water to make 16 hydrogens. Now I have to consider the oxygen in both of these products. I have to get the total. So here I have 14 oxygens in carbon dioxide, and 8 from oxygen for a grand total of 22, so I put a coefficient of 11 in front of oxygen. Last 2 examples. Here I have 1 sodium. Here I have 1 sodium. So at the moment, sodium is balanced. Here I have 2 chlorine, but over in sodium chloride, I only have 1. So I got to put a coefficient of 2 in front of sodium chloride. That now gives me 2 sodium. So I put the 2 in front of sodium. Again, you can check to ensure that we have the same number of each element on both sides. Finally, here we have our double replacement reaction. We'll talk about different types of reactions in the next topic in this unit. Here we see polyatomic ions. I see the polyatomic ion phosphate and the polyatomic ion carbonate. Now, just like it's stated on the helpful hint slide, instead of individually balancing phosphorus and oxygen and carbon and oxygen, as long as the polyatomic ions don't change in the reaction, you can balance them as a whole. Notice I have phosphate, PO4 on the reactant side, and phosphate, PO4 on the product side. All right, so let's go ahead and start balancing. Here I have 3 sodium atoms, or ions I should say. Here I have 2 sodiums. So again, we have 3 of one thing and 2 of another. So I put a 2 in front of the 3 and a 3 in front of the 2. That balances sodium. Now, when I look at this formula, I have the coefficient in front of sodium phosphate, so now I have 2 phosphate ions, which matches what I have over here. So now we're going to move on to calcium. Here I have 1 calcium, and here I have 3. So I have to put a coefficient of 3 in front of calcium carbonate, and that gives me 3 carbonate, which I have over there. So now we can go ahead and check 6 total sodium, 6 total sodium, 2 phosphate ions, 2 phosphate ions, 3 calcium, and 3 carbonate, 3 carbonate. I'm going to pause the video a second and answer this phone call. All right, moving right along. Sorry about that. Here, I got these transitions here. All right, so now we're going to talk about reaction rates. So let's look at this. You got a large beef roast in the refrigerator. Your family is hungry and it doesn't want to wait for hours for dinner. So what are 2 things you could do to make it cook it faster? So look at this. Raise the temperature. I can't even spell right now. Teaching is hard these days. I could also cut the beef into smaller bits. Cutting the beef into smaller bits is another way of increasing its surface area. So these are things we could do to cook the roast beef faster, so increasing surface area. So I keep talking right at the same time. So these are just 2 of the 4 things we can do to make a reaction rate go faster. Now, cooking, is just a chemical reaction. If you want to make cooking faster, you're making a chemical reaction faster. So these 2 things are things we can do. All right, so let's talk about why rates of reaction are different. So rate of reaction is just defined as the speed at which a reaction occurs with reference to the loss of a reactant or the gain of a product over time. So it's just the speed at which reactant concentrations decrease and product concentrations increase. It will always be expressed as some kind of change over time. And you actually have seen this. We refer to the rate of travel in a car or while we're running or whatever as miles. Darn it, I always hit the wrong thing when I'm making videos. As miles over the number of hours, or miles per hour. The change is the distance we've traveled. The time is the number of hours it took to do so. So there are 4 factors that can influence the rate of a reaction. We've actually looked at 2 of them already. So one of them is changing temperature. Faster temperature gives faster reaction. We could change the concentration of the reactants. We could increase the surface area, or at least change the surface area of reactants, or we can add something called a catalyst. All right, so collision theory is the theory that explains chemical kinetics or reaction rates. Collision theory has 3 main principles. 1, in order to react, reactant particles must collide with one another. They have to come in contact with one another. Now, they have to collide facing the correct way, or in the correct orientation. And they have to collide with enough energy to overcome activation energy. And we're going to go ahead and define these things in the next slide. But your goal is, we're right here. Your goal is going to be to use collision theory and the tenets of collision theory to explain why those 4 factors change the rate. So activation energy is essentially just the minimum amount of energy that you would need to get a chemical reaction started. All right, so let's talk about concentration. Concentration is units per volume. So more concentrated means more units in the same volume. So let's go ahead and draw 2 two-dimensional squares here. And they both have the same volume. In the box on the left, I have 1, 2, 3, 4 reactant particles. And in the box on the right, I have 1, 2, 3, 4, 5, 6, 7, 8, whatever, blah, blah, blah. Let's do a whole bunch of them. So let's go ahead and call this one box A and this one box B. So you have to remember that I kind of drew these as static dots. They're not moving around, but in actuality, reactant particles are always moving around. Now, a reaction doesn't occur unless they collide with one another. So the question becomes, where are collisions going to be more frequent? In box A or box B? Well, think of it like a highway. The more cars you have on the highway, the more likely you are to collide with other cars. So increased concentration will increase the reaction rate. The reason why, oh, come on now. The reason why it increases the reaction rate is because you have a greater frequency of collisions when things are jammed closer together. So I'll say when reactants are more cramped. So the effect of increasing concentration, the rate of the reaction will increase because you're going to get a greater frequency of collisions because all the reactants are crammed into a smaller space, or they have less free space to move around. All right, now let's look at surface area. Now again, we're going to do this all in 2 dimensions because my art skills are lacking. So here, let me make this bigger actually. I'm going to have a 2-dimensional square drawn on the board here. And this square has sides with length 2. Now, if reactants are going to collide with this square to make the reaction happen, they can only collide with the outside surface. But let's say I take that square and I break it into 4 equally sized pieces. So if all the pieces are equally sized and the original square had sides of length 2, then each of these individual squares have sides of length 1. Now, reactant particles can still access all the space they could on the outside, but they can also collide on the inside. So I'm going to try to do this with symbols just to make it go a little bit faster because the video is running long. So increased surface area or smaller pieces means you have an increased rate. The reason why is because there's just more surface available for colliding. So I'm just going to say the reason is more available surface. There's always a tug of war between making a high quality video and making one that's not too long. All right, next, increasing temperature. Well, remember that temperature is just basically a speedometer telling you how fast the particles are going. Now, there's that thing called activation energy. When 2 reactant particles slam into one another, so when one going that way and the other going that way, when they slam into each other, the collision has to be energetic enough to overcome that activation energy. So let's just make up some random numbers here. Let's say these particles here are heading toward one another at 10 units of speed. If I have 2 more particles moving toward one another at 30 units of speed, which is going to result in a higher energy collision, the faster speed. So the faster you're moving, the greater the chance you have to overcome the activation energy. So increased temperature means you have faster moving particles. That means you're going to have an increased rate or a faster rate. The reason here is actually a double reason. There's 2 reasons. One, faster moving particles just means more collisions or a greater collision frequency, but also they're going to be faster. higher energy collisions, which is more likely to satisfy the activation energy. Almost done. A catalyst is just a chemical that we add to a chemical reaction to increase its rate. A catalyst works by lowering the activation energy required to get a reaction started. So a good example of a catalyst, this isn't actually a true catalyst, but using an accelerant to light wood on fire. You can't take a log and light it on fire just by throwing a match on it. The match doesn't burn with enough energy to get the log going. But if you cover the log in gasoline or lighter fluid or some other kind of accelerant, that will get it going. That is not a good example of a catalyst, but it's the same general idea. It's something you add to make it go faster. All right, now this means that the particles just don't have to be moving as fast in order to collide successfully. So a catalyst can help you maintain the rate of reaction at a lower temperature, or just make the reaction go really fast at a high temperature. A good example of the use of a catalyst is the elephant toothpaste reaction from Discovery 5.1. And that's it, kiddos. I hope you have enjoyed this video. If you have any questions, please bring them to class, and I will see you for the next one.